is what they do. Okay, that's why they're an acid. And so since all of this happens in water, yeah, it all happens in water, right? Which form are these things going to be in? They're going to be in the conjugate base form, right? So you may hear me say, and you may read, and there's nothing wrong if I would have said pyruvic acid. Okay. There's nothing wrong with me saying pyruvic acid or citric acid, but do you ever really have pyruvic acid or citric acid? No, you have its conjugate base, which is pyruvate or citrate. So that's the difference there, just so you kind of keep that in mind. It doesn't matter, but like I said, you'll hear me go kind of wander back and forth between the two terms, but I should keep it kind of constant. Now, so that's the conservation of the carbon. With regard to some of the energy that's happened here, what have we seen? Somewhere in here, and I'll show you exactly where in a minute, there are a couple of places where oxidations occur. And you should be aware, if you have an oxidation, you must also have a reduction, right? And what is our most preferred thing that we want to reduce? NAD to make NADH. So if I tell you that happens twice, you just have to trust me. We're going to get two NADHs here. Now, by the way, where is this happening in the cell? Cytosol, right, in the cytoplasm. So just in what cells in the body? What? All of them. All of them. Okay with that? And there are two places here where, well, in the net sense, as we'll see in a minute, it's actually happened 4 times, but where ATP is produced. Meaning that the energy, somewhere there's some release of energy from the breakdown of glucose so that we actually can drive the synthesis of ATP. We call that substrate level. And the net ATP production, as we'll see here in a few minutes, is 2 ATP. Tell me about temperature here versus here. I just asked you, do you have to release heat? And you have to release heat. So where did the carbons go? 6 carbons came in as glucose, 2, 3 carbon containing pyruvate. What happened to energy? Energy came in as glucose. Now we have energy in pyruvate, energy in NADH, energy in ATP, and some energy lost as heat. Where's most of the energy? Still in the pyruvate. Still in the pyruvate. If you don't believe me, pyruvate is what fermentation breaks down and uses. And what does it get from it? Ethanol. Is there a lot of energy in ethanol? Did you ever light it on fire? Yeah. Oh. So this still has most of the energy. What's usable energy at this point to do some cellular work? 2 ATP. How efficient are we really at this point? Not very, right? We started with, at the most, 686 kilocalories right here. If I blow up glucose, it releases 686 kilocalories. This right here represents about 15 kilocalories. That ain't very good. So it would be to our advantage, right, to have a mechanism that would allow us to extract even more energy from pyruvate. We don't care about the NADH at this point. It's still got some energy in it, but this is where it's at. The enzymes that are capable of catalyzing the reactions that allow us to further, I'll use the right terminology here, oxidize pyruvate, are found in the mitochondria. So where does pyruvate have to go at this point? Into the mitochondria. So if I want to use it right, now from the cytoplasm, this pyruvate has to get transported into the mitochondria. Just so you're aware, this pyruvate goes into the mitochondria by a process of diffusion. It's actually facilitated diffusion. We have to use a protein carrier to help it, but we don't have to add any cellular energy to move it in. Why? Because it's in a really high concentration in the cytoplasm, because that's where it's being produced, and it's being consumed as soon as it gets in the mitochondria, so it's always going to be really low in the mitochondria. So there's always this gradient, if you will, pulling the pyruvate in, so it's not difficult to get pyruvate into the mitochondria. Okay with that? Now, I want to feed this into ultimately the citric acid cycle, but I can't feed it into the citric acid cycle as pyruvate. You'll see in a few minutes, the citric acid cycle can only receive compounds that contain 2 carbons. How many carbons does pyruvate have? 3. So I cannot feed a 3-carbon compound into the citric acid cycle because it can only receive a 2-carbon compound. So I have to do something to pyruvate before I can get it into the citric acid cycle. And one of the things I have to do with it is remove what? I need to remove the carbon. So this happens actually, it's a few steps where this occurs, but I'll kind of summarize it here. I have to remove the carbon here. Now if 2 pyruvates come in, this happens, this is all, I'm going to just do this. Everything that we talk about here is times 2, right? Because each one of these pyruvates has to have this happen to it. Does that make sense?